We are streaming. Oh, you gotta switch back to your code editor. Okay, let's just double check that I can see the stream. Let's see.
Now I hear it twice.
Oh wait, I think I sent you a link on Slack, so let me just see if I can open that. See if we're live.
I hear you twice now, Daniel.
You hear me twice?
And then I
Okay.
hear me a while.
Ooh. Like now?
No.
Okay, I think it's because I opened the video. So we are streaming.
Yes. Yes. I
There we
actually
go.
hear myself.
You hear yourself.
Yeah, I hear myself. Like I think my voice travels to South Africa, and then it travels back. So
Okay, is that bad?
it takes 5 seconds. Yeah, because I hear me very loud, so I think I
I wonder if that's...
I can't really think.
Yeah. I don't know why that is. Let me... And now? Can't hear me at all. I wonder if it's my microphone.
Okay, I'll say something, and if I don't hear myself in 5 seconds, then no, I hear myself. This is crazy, actually. But we can try with this echo. But if
You don't have the stream open
no,
anymore, do you?
I can't. Oh, maybe I have. Good. Yes.
Oh, okay. I was like, that makes no sense.
Now
Okay,
then.
there we go. That should be good.
Okay.
Cool.
Super.
Okay, guys, this is only our second stream, so I don't think it's that bad. For
Yeah, we're learning.
Yeah, we're learning. I'm just going to check to see everything is okay. I still wanted to find a way to check the comments. Cool. So then
Do we have any viewers?
we have 6. We have 6.
Oh
viewers.
my God, that's a record, right? Most,
Yeah, we
that was
basically
5 last time.
2 ninjas. Okay, well, okay, let's start. So last time we were working on the Sieve from scratch. Oh, hi Eugene. I haven't seen you in a while, so let's. How's it going? So last time we worked on a Sieve, and we actually we managed to sieve out prime numbers, but we had an issue where if the input was a prime number itself, then it wasn't included in the results. We're still going to carry on with that bug, and we're just going to try and improve the performance of a sieving an input of 1 million, because this video is about performance, not about accuracy.
Yeah, something like that.
Something like that.
Yeah, let's not get stuck on that bug for now. We can fix that later. We are going to save to 1 million, and our code works for even numbers, so that's fine for now. Hello, everyone. Every 6 of you. That's awesome. Let's see where I want to start. I hope you have you at least know that there's a repository for this on GitHub. You can see the link below the video, and you can choose on that repository. There is a branch of it that's called Livestream 1. Yeah, Livestream 1, where the code is like last time when we left off. So, but you can also check out the master branch, and there the code will be more of a blank slate. So that's your choice. But if you want to play with zips, this project is prepare for it. And let's see, we have some facilities in this project that I haven't mentioned yet. Last time we were performance testing stuff using Criterium, and we could performance test this Sieve vector to let's see here. This Sieve vector, and we could quick bench, use the Criterium quick bench to see the performance, sieving the first million numbers. And if I remember correctly, we were down at 0.2 seconds or something, 200 milliseconds. So was that correct? And remember when we started this, we had something that took like 5 seconds to sieve. So in last episode, we actually cut a lot of that, orders of magnitude. Yeah, so now today my Mac is happier, I guess. So we're actually down on 136 milliseconds. So yeah, I don't know, but it's this is about where we are. You need to run even quick bench several times to get super accurate numbers as well. But in this project, we actually have one more way to benchmark this, and this benchmark function down here, and that's what's used when this is benchmarked in this drag racing competition that we've been talking about. And so there they run this program, or a program like this, in Docker, and they do that for all. I mean, I think there are over 300 programming languages now in there, and yeah. So they run this, and it has a special output it should have, and we format the results here, and we have some config here, so we can run our first sieve, the set sieve. So this called just sieve, I think. Yes. And
that's the initial sieve that we started with.
That's exactly. And it has a count function. And since it was using just a set, we can just count. And it needs to report here how many threads we're using and how many bits. In this case, we don't know how many bits, so it's and then we're running it here. So we have here in this rich command a few. So we can run this with warm up true. That means it will run it for 5 seconds, not counting, and then it will run and count how many times it does it. So it passes 47 times in 5 seconds. That solution, which is cool. Pretty good. I don't remember it being that fast actually.
But like last time I remember it took like 5 seconds to. Your computer's on fire today.
I don't really believe it.
No.
Let's see. So yeah, with the experiment we did before. So now I reevaluated that one. So let's try it now. Again. So it will run 5 seconds. First, not counting. It's a sort of warm up of stuff. No, it runs in. I don't get this. Let's run it with warm up false here, just to take 5 seconds then for us to get an answer here. 2. Maybe I needed to reevaluate this one as well. That's I think what was happening, because I know the warm up is not making that difference. So now it makes 2 passes. It says in 5 seconds, and it's actually the average time here is 2.6 seconds that we're doing it. But I think that is actually me just dividing this by 2, it is actually taking almost 5 seconds. But then we cut it off next time. So I think that's what's going on here. But I'm not sure. But anyway, it's 2.5 seconds. So that's pretty slow compared to our new one. So I was thinking that we could have the new one also configured here.
Okay.
So if we copy that configuration, and then we have our vector sieve, right? Oh, I copied it for a reason. We have our vector sieve, and we call it sieve vector, and it will need another way to count it. So we will have our vector of Booleans, where every prime will be represented as true. So we should count filter true on the primes. So that should be the function. And we're still just using one thread, and we will not go to multi-threads, I think, in this stream, at least not today.
Okay.
But we are actually still, we don't really know how many bits are being used. This is a mutable vector with all this memory sharing and stuff like that. So actually, it's correct still to say a question mark on that one. So now we have defined that one, and we should be able to run it. And there, 48. So that we was actually running this before. So that's the improvement we have made.
Sorry,
in terms of this benchmark.
We got a comment that Uncle Bob also actually has made an implementation of a prime sieve, and he did it in Java.
Okay.
I just want to say that your Clojure solution is now faster than the Java solution.
But he did. Yeah, well, it's easy to do something a bit naive, I guess, or because I have also done a Java version of this zip, and let's see if we can find it here, and it's this one. It says this was the original code, but I actually just replace that with a translation of my fastest Clojure sieve to Java.
Okay.
And it on this machine, which is a very fast machine that it's running on, but I think it's comparable to my machine. It does it 14,000 times over 5 seconds, and my fastest Clojure one does it. So it's a bit. I can't say this for sure, but I think what we're seeing here is the overhead that we get from being a level above Java. But don't take my word for it, because I have had so many different results. It's very hard to keep everything, every variable stable here when you test these things. So it's you need to be insanely focused on the details and everything that could be moving. But anyway, so that's it's possible you can implement this in so many ways, and we will see that when we continue here, that we should be able to improve on this performance we see here. But anyway, now we have that
we got
set
the
up
results
there.
Yeah.
So then we should be able to run the run script here that we have, and I hope it won't be running it many times. Let's see. Let's look at no, it's just one.
Okay, so
and then it will run. It will run both the set one and the vector one because I had prepared that. And so now it ran the set, and then it crashed. It might be that we have some duplication and stuff like that in this file. I think we will find out when we look at the code we have here. So let's not worry about that. But anyway, I'm thinking if we can set it up so that we can run this script when we have a few solutions, then we can get this answer quickly for how, because this benchmark is of course not as accurate in a sense as the criterion one is, because the criterion one does much more than just warming things up. But it's a good way. So if we get it working, and we will commit this working code to the repository again, so people will have something
when we get it working.
Play with.
So
when we get it, I don't know why it crashes now. It's just like Sieve is null. It says that's a bit strange. I think, but we can get it working. But let's go on with the sitting for now. So here is where we were last time, and we have this Sieve here. Someone asked if why we were starting at 3 last time, and I think I was like, I was not. I was thinking about this bug and everything, so I was blocked out. But anyway, the reason we start at 3 is because this loop, even though we are using a vector that only contains the odd numbers, remember that we have this vector is 500,000 when we run it with 1 million, we are still looping over all the numbers. And we know that 2 is taken care of already. So the next number we should start with is 3. That's and then we cut it in 2 here, or we increase it with 2 and stuff like that here. So that's the reason. This loop is still considering like 0 to 1 million.
And the reason 2 is already taken care of is because 2 is already set to true, and you bypass 2. So you have the array, and the first vector in it is already true.
Yeah, exactly. You can say that. But also 2 doesn't really exist in this array. We treat the index 0 as 2. But it's already set to true, so you're correct about that. Okay. But that's our 2. It's if you look at this array and you will actually realize that it would be the number 1 and then 3 and then 5, and in this but we treat the first one as the 2. That's our special trick here. Okay, so I hope that I didn't make it even more confusing about the 3 here, but that's why we started 3. And let's think about what we could do to this one to improve performance. So you have kind of several things. We could be doing something that they call boxed math, and if I am understanding that correctly, it is when the math, like when we add stuff or multiply stuff, and it's not translated directly to Java as p times 2 and stuff like that. Or it is translated to some class which has a member method which can multiply things. It's overhead in it, and I think that's the box, right? It boxes it in an object and stuff like that. And we also have something called checked math versus unchecked math. So Clojure is very helpful with the math operations. It does, so it can check the numbers for you, that they are in the range, allowed ranges and stuff like that. So, but if you know that we're not going to give it any such numbers, we can use unchecked math as well. So that's we have something here. We also have reflections, of course. So if we're doing like Java interrupt, like we are doing here, no, we're not doing so much Java interrupt yet. But anyway, you can get the Clojure compiler to have to use Java reflection to figure out the type of something. That's a bit probably not only about Java interrupt. It's just like you can help the compiler with type hinting. So you can tell it to warn on reflections, and you can also say that when we have box math, we will also want to be warned.
So just sorry.
If we put that here, yeah.
So that warn on reflections, that will just put a warning every time it's using reflection, and then you can type hint. You can set type hints on those at those places.
Yeah. Let's see if we have something like this in this one. No, we have warn on reflections through here. But we didn't get any. But if we see this box math thing here, we probably have some box math.
Okay.
In this. So it says on line 73 and 75. So this one ends up comparing this in this boxed way. We can, so it's not going to translate this to straight Java, n is less than 2. It's going to do it in a very roundabout way. And on line 55, this halving of n will also be boxed. And on line 84, this comparison is also in the box. And that we lose time there. So that's good to know. Let's see here. We also have unchecked math.
Sorry, Peter. If you can close your file.
Yeah.
If you close your file explorer, then I think we can get some more real estate on the code. Yeah.
Cool. So we say, I think it could be set that to false. I don't remember where it starts. Okay, now we have no complaints. So let's. Okay, that was that one. Sorry, I'm a bit confused. Here. So anyway, so we know now that we have box math in here. So that could be one of the places where we try to improve the performance. But we also know that we're using this immutable vector, and maybe we can help Clojure better by thinking about that problem. Because here, every time we do this Hasus here on the primes vector, we will create a copy of that vector in Clojure smart way. But anyway, that is going to cost us. So then Clojure has something that's called transients. So we could, if we want. Which one would you want to try here?
Let's start with the transients, because I think that would be...
Yeah. Yeah, that's an assumption, but I also think that when we get down the performance more, or up the performance more, rather, then this box math will start getting to be the problem. Right now, I don't think it is, actually. So let's see what we can do here with transients. I just copy the vector sieve, cool. And we say sieve vector transient on this one. And the way transients work, we could set this up to I have so fat fingers today, I don't know why. There, and say transient on all those. So we just see that everything still work as before. So if we sieve this 200, we still have
25
there, and we can sieve it to 1 million, and it will do that for us, so that we know that we are on this working state. Yes, we are. And the way transients work is that you can just tell Clojure to create a transient vector by calling the transient function.
So you
if
call
we look at the transient function.
Yeah, I know. Okay.
So it will return a new transient version of the collection, and it will do that in constant time. So that's good for us. And they have some examples here. So you can see this vector v here is transient, and then instead of conj, you use conj bang. And then when you're done, you need to get it to a persistent vector again, and then you call persistent. Persistent is the word for these kind of data structures that Clojure is using. They are immutable, but the actual name of the kind of data structures is persistent. So we call transient on this here.
What happens? Sorry, I'm just curious. What happens when you call persistent on a transient vector?
It will convert it back to
okay.
It will convert it back to an immutable vector.
Ah, okay.
So you will only have like a transient vector inside your logic, right? But to the world outside, you will return a persistent vector or an immutable one.
Okay.
So we will do it on this one. When we're done, we will return a normal immutable vector, not a transient one. Are you following?
Yeah. So that last primes will.
So here we have. So we have a transient. Primes is now a transient one. That means we can't call asus. Do you say asus or asuk?
I think it's a soch. But
asosh. Okay,
yeah.
Asosh. Is that South African? Asosh?
No, that's
or
like,
is it, okay.
Alan told
okay.
me that that's what it is. I used to call it a sock, because that's how I would say it. But it's a soch. Because it's associate.
I say associate because it's associate, but you say associate. I see. Okay.
Yeah.
That's my broken English. Okay, so then you can't associate on it. You need to associate bang on it, right? Because that will actually mutate this vector. It will not keep creating a copy. It will mutate it. And then when we return it from here, we call persistent. And in theory,
That's it.
that should be all we need to do to get more performance. So let's see that we still seem to have the right thing. Yes. We could time count to this looting. It's still answering the right thing. And now do the quick bench here. So you saw that time, including the looting, was faster here than our earlier benchmark. So
Yeah.
it kept like down to a third or something like that.
Yeah, that's
what you can gain with transient. So it is a bit more to do here, and keep in mind that you're actually now using a mutable thing. I think you still have some help from Clojure to maybe someone in viewing this knows if it's still like how thread safe it is or whatever. So that could be good to keep in mind. And at least now you're actually mutating things, so it's a bit more. So sometimes I think I said in some video talking with you, Daniel, that people don't use transients, but I think I spoke out of ignorance there, because sometimes they really make a difference, and then if that difference is important to you, of course you should reach for transients. That's why they are there.
Yeah.
So that's fine. So we by just adding transient here, a bang here, and persistent here, we gained a third of the performance. But this code is a bit hard to read, I would say, and that's not Clojure's fault. I would also say, because what we're doing here, we reach for loop, remember, instead of recurring or using regular collection functions and stuff like that. So the code gets a bit. I think that Eric Assam would say that we are writing Java in Clojure, something he doesn't recommend, but. Sometimes, so that's one of the reasons that this looks a bit dense or hard to see what's going on. But now that we're using transients, we can actually get rid of some of that. We're doing like Java in Clojure, so we can take advantage of that to get it a bit more readable. And do you see how?
Not off the bat.
Someone in the audience see how we could make this what we're doing here that we don't need to do?
Oh, you're saying that we don't need to do anything?
You don't see it.
I think the problem with the audience is that I think our stream is also very delayed. So it's not an instant.
Yeah. No. It can also be that they don't see it. You don't see it, right? So it's. I can tell you, we are passing this thing back in our loop all the time. Here, so we are recurring here, giving it primes, right?
Yeah.
And we are binding it here in the loop all the time. But that's what you need to do when you have something immutable, right? You need a new copy into the loop. But now we are mutating it.
Value.
We are updating the value. We're just sending this thing now for nothing. I don't think it costs performance, but it costs in reading this function, right? Do you agree?
Yeah. So I'll be curious to see how you want to.
So if we move this out here.
Oh, okay. And you just create the initial let binding, and then we're updating the state of primes. I see. Okay.
And then exactly. And so we are updating it now, and we are then recurring with with it back here. So let's see. Here we recur with, so at least we should what should we do here, Daniel? We should, if we should do this, we should ASUS, right?
Okay.
And actually, that is like a when this happens, we should ASUS. And then when we recur, sorry, we don't need this thing, right?
Oh, because we don't need to pass.
So we ASUS. Okay, so that's actually here. That's why it's complaining. I got confused. Here. Okay. So we ASUS and then we recur. We don't give it back.
We're not passing primes anyway.
The primes, right?
Yeah.
And here we don't need to pass primes either. So, quick. And here we do a recur. If we should be doing this work, we do the recur here. So actually, what we should do, I think, is to just see if I did that right now. When this again, this if here. When p is still equal to this less than the square root, then again when it's not a prime, we should loop, and at the very end of that, we should recur. Let's see if that's correct. It doesn't look correct on this one.
Is it in the loop? Oh, it's in the.
I can only use in the tail. In the tail. So actually, we're not in the tail here. So we do the loop, and outside that loop, we can return the persistent version of the primes.
Actually, there's a comment here from. I won't attempt to pronounce the guy's name, but he says he actually prefers the loop version where you bind the primes, and that makes it explicit.
Still?
He still prefers that version with the immutable passing of primes to make it explicit what depends on what.
Is he talking about he prefers this version, or he prefers this version?
Yeah, the top version with the loop.
Even okay. When you loop back the primes.
Yeah, but I suppose at this point it does become preference, hey?
Yeah, I think that is a preference. To me, this is like less code to read and follow along. So I see here that in the left here we do a transient version of it. We haven't checked that this works yet, right?
No.
So we should do that, I think. That looks correct.
Yeah.
And that looks correct. And we should still have the same performance, I think. I don't think it costs anything to loop back the primes, and it doesn't. So whoever viewer is there, if he or she prefers to loop it back, then that at least doesn't cost anything in terms of performance. So So I think it's a preference thing. I don't particularly need it to see what's going on here. It's more like this is harder for me to read.
Yeah.
Than this. This starts to get very similar to how the algorithm is described on Wikipedia. So you can see that if as long as you are below the square root of n, and if the number is not is a prime, as long as it is not a prime, you just loop over it. When you reach something that's still marked as a prime, then you know that it is a prime, and you know that all the multiples of it are not prime, so you mark them as false. I think that's very straightforward to read this. So, I mean, big success.
Yeah.
Even if this last thing was needed or not, it's still the performance gain. We got that one right.
Yeah.
So if we would then in this. Let's see. We put the transient version here on. Transient. Was hard to type. See better transient. Still the same count function. And one thread, unknown number of bits. And if we evaluate that, and we have two identical, I think we use this one, right?
Yeah.
So if we run this with warm up, it will take 10 seconds. We should see more than 47, right?
Yeah. I just want to say,
we should see
the more code parsing with your eyes. I remember that there's Richard Harris, he made Svelte. I think he once cited there was a study once that no matter what language you're using, the more lines of code there are, the more likely they are to be bugs. Like the bugs are in proportion to the lines.
Yeah, you mean you're still on debate here?
I just remembered that stuff. Which I thought was interesting.
I think that's very something that's often said about Clojure. I mean, when you write the same program in Java as in Clojure, at least when it gets non-trivial, you have many more lines of Java code than you have Clojure code, and that translates to less bugs. So that's been said also in the Clojure community. Now, someone should tell Rich Harris about Clojure. So it would be awesome if we could make a Svelte Clojure script version of it.
You heard it first.
That would be. I mean, I don't say I played with Svelte, but it's awesome. I mean, it would be great to have it in Clojure script. So again, we need to ask ourselves, how can we improve this performance? How much time do you have, would you say?
Well, I actually don't even know how long we've been streaming for. Let's just see. We've been streaming for, I think, an hour or 50 minutes.
Yeah, less than an hour. Yeah, exactly. I don't mind. People watching streams, they should be used to that it can be long, right? But just more like your time.
Let's do one. Let's do another.
I don't mind.
We've already improved the speed 3 times. Let's do it again. Let's improve it some more.
Yes, let's improve it some more. And again, I think that I could be wrong. I don't think that we will gain all that much yet by thinking about the box math and stuff like that. Because in 5 seconds, it only passes 162 times. So that means that it's I think that we have more to gain by, again, thinking about the actual data structure that we're using. And so far, we've been using Clojure data structures. We all, as Clojurians, of course, always prefer to be using the immutable ones and everything like that. They've already broken that rule and reach for transients. But you can reach for native Java things as well. You can do, of course, you have all the whole Java ecosystem and the standard library and stuff like that. We have bit sets and stuff like that that might be good for this problem. But you also have the Java version of our vector is just an array of Booleans in Java. So let's call them native Boolean arrays. And that's very quick to update an array in Java.
Okay.
So what we saw here, I think, when we moved from immutable to a transient version of the vector, was that it's the update of the data structure that takes time. It doesn't take time to do these comparisons. It takes time, of course, it takes time, but it doesn't take as much time as updating the transient vector. So a guess here is more than a guess in my case, but anyway, is that Boolean arrays are much faster. So should we try to do it with a Boolean array?
Yeah, let's try and do that. So
yeah. So again, I will just copy all this code. Now the loot function might stop working for us, so we need to update that one. But we can now say Boolean array here. And this is a Java array of Booleans. I mean, in Java, I think it's called like that, right?
Yeah.
The data type. So we should be able then to, instead of the transient here and the vector, should be able to do a Boolean array. And we fill it. In this case, I don't think this will work. It is a Boolean array.
So the Boolean array needs has a set size.
Yes, yes. In Java, you say what do you say? Boolean and brackets and the size, colon, and then the name of the array. I think, right? That's I remember correctly. That's how we say. So this will then hopefully then translate into that kind of code. Right? So you say we want an array of Booleans, and we actually should see here size or sec size init val. So it takes an init value as well.
Okay.
So we want them to all be true. Like we assume they are all primes, right? That's the start of this thing then, and then this is the same. We loop from P3, and this is the same, but we don't check like this, I think. with a Boolean array, you would instead say array get.
Oh, okay. So that
Works
would be,
on Java arrays of all types.
okay. So that would be the same as like calling .get on the array structure in Java, I assume. And it takes an index.
Yeah, actually, you will just use bracket in Java,
yeah.
right? You say primes brackets. So that's how you index it in. So this hopefully gets translated to something like that again. And then we loop. I guess it's the same way as we did before. And if when we're still not at the end, we should then update this value. So then that's offset. Instead of a sus bang, we offset.
Cool.
Yeah, array set, exactly. And otherwise the signature is the same as with a sus bang. And we recur back, and then in this case we return the persistent primes, but in this case we should let's return just this Boolean array, because again I'm looking at this drag racing competition which allows this. So we will not put the work of actually looting the sieve into the time.
Yeah.
So we have our loot function here instead. So this should then do the same thing as the other one, but just on so if we would call this on 100, we get this out. It might be correct.
So
we're calling
25
the
truths.
So that's why we.
Yeah,
I think it was this error copy paste bug.
It's like
Boolean array. Not zip.
Isn't it
Sorry.
Isn't it a Sieve Boolean array?
Exactly. There. So if we call it like that, we should get. If we call it like that, we get like an object back. So we need something here to loot it that looks a bit different than what we have here. So I think it looks like very, very similar to this one. Maybe it even works as this. Because in Clojure, even the Java arrays can sometimes have the same structure. I didn't call loot, right? Sorry.
No.
So if we call loot there, it is the same.
Sorry. So you're saying that Clojure will automatically treat the Boolean array like it would any kind of like vector? Okay.
Yeah, that's what I'm saying. So this keep indexed when it sees a Java Boolean array, it will do the right thing. Will pick one item at a time from that collection.
Oh, cool. Okay, it's good to know.
So I mean, that's at least what it's doing here. Let's see. 81 milliseconds. That's fast, right?
Yeah.
But not as fast as.
Yeah, didn't get it at 40.
1 millisecond, Daniel.
Yeah, that's pretty quick. Yeah, that's why you don't use time for your.
Yeah, now we're actually looting it and stuff like that. I don't think that takes this insane amount of time.
Okay.
To do it, but it's I think it's this actually this thing here now that costs for that thing. But doing it within the rules of this competition, we're allowed to return whatever data structure we used for the Sieve.
Okay, so now
it's 1 milliseconds. So we were down. We were starting at like 2.6 seconds, I think, and then we saw something where we had it at 200 milliseconds, 100 milliseconds today, right? And my machine is on fire, and down to the transient one ran in like 40 milliseconds, right?
Yeah.
So this is much faster, and now maybe also we are actually seeing the impact of this box math and stuff like that.
Okay, so should we go there next?
We could go there next. If we look at this thing I was showing you before, you see that we can actually get it to run very, very fast. So we could go there next, and then if you feel we have time, we can. We have some facilities in this project again. So I have made some snippets that these when you call these, they will send this code to the Repo. So this is a Calva thing we have here. So what I will do is I will require CLJ Java decompiler, and we'll have a link to that in the repository. I know there is one. So, and we will decompile whatever is the top level form. And we will do a string of that, and we will spit that out to a thing that is named the same as the thing we're defining in the top level form. So if we have a function that's called Sieve, then this variable here will contain the string Sieve. So it will be the compiled sieve.java.
So would that take what gets compiled and decompile it? So it will get compiled into Java.
That's good. So so Clojure compiles to bytecode directly. It's not compiled to Java. It's compiled to bytecode, and there is also a Clojure runtime that's sometimes being used from that bytecode. So it's a little bit of a mixed between a compiled language and a runtime on top of that. But if you can think of it as compiled, most of it is compiled to bytecode, and then that bytecode is decompiled by this function. If we look here, we also have some that's called disassemble, the top level form. So that will actually allow us to look at the bytecode that is compiled. So if we would send this to the compiler, so if you do Control-Alt and then space and then space again, use Control-Alt space, then you get a menu with a defined custom snippets. And now you get some duplications here because I both have them in workspace and in my user settings, because this is a merge of those. So I hope this still works this merge of this. But anyway, so here we have this disassemble. And I have bound that to the key B, which means I can also press Control-Alt space and then B to run it without going to this menu. We can just do it from the menu now. And was reflection warnings, which is interesting. And then if we show here again, it will have created this file here. And this is the byte code that is being compiled from our function. You can see here. I don't know what you can see here. Actually, it was, if you were like me, Daniel, this is a bit hard to read. Yeah, I have been coding in assembler when I was a kid, but that was a long time ago. And since then, I've been mostly high level. So I have not studied Java assembler at all. But anyway, you can sort of, if you squint, you can sort of see a bit of what's going on. So this is the code then that is decompiled if we use the decompile one instead. So if we say decompile here, then we will get a .java file here instead. And I will put it side by side here so we can have it side by side with our function. Here you can see, I think, a lot of how efficient the Clojure compiler is, and because this code is very similar to this code, right?
Yeah.
So you remember when I reached for loop instead of something else? I said that is the closest you can get to a native performance, to Java performance from Clojure, when you need to iterate over something very quickly. And the reason for this is that it actually gets translated to a Java format.
Okay, cool. Yeah, you can see it's quite readable actually.
It's quite readable. You can see here that it casts this thing using the runtime. And here it casts this thing using the runtime. And this takes time because these are calls into functions that have a lot of branching and testing and stuff like that before they. It might take time here to cast this thing to an int because the runtime needs to do some checks on it in order to do it. So we want these casts actually to be native Java casts. But we'll get to that. One thing you have in the toolbox is this unchecked math. So we can see here that to multiply p, it's numbers multiply. And numbers, I think, is from Clojure Lang as well. So if we do, before this Boolean array here, we set unchecked math to true. I think actually that should be a Boolean or not. Let's try it. We set it to true.
Yeah, I think it should be a Boolean.
Here. Maybe you can see it here. Well, bound to true, compilation of plus, minus, star, blah, 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 will be done without overflow checks. So true is the value we should have there.
Yeah.
And now, if we decompile this, and now I will use the shortcut, Control-Alt-Space-T, and it will update this here. And I'm not sure. Let's see if we undo. You can see what it does. Unchecked int cast. It does instead of int cast.
Oh, okay. Yeah. So you can see the rt functions changing.
So in unchecked double cast, and it does a couple of those. So we know that it might be time to look at this decompile code and figure how we could help the Clojure compiler to do something more direct with it. That doesn't go. So one thing we could do is uncheck math to true. That might or might not gain us.
Well, we can see, I suppose.
But we haven't compiled it with this unchecked math to true. So now we do this.
So we were at 1 millisecond before.
Yeah. Okay, so I'm not completely sure here that we are actually seeing this huge gain from unchecked math, but we might be. We can, of course, try that. But setting this to false, compiling this again. It is a bit also about how the machine is feeling at the moment. So how it actually took 3 milliseconds. It could be. We were down on 1 millisecond, right?
It was at 1, yeah.
2
That was the last one. So okay, so this is getting a bit faster.
Well, one thing that I have noticed, and this is important, I think, is that when you have compiled and recompiled and done this a lot of times, then actually the REPL starts to get a bit funny when it comes to the numbers. So let us restart the REPL. That could be the reason why it's so the funny numbers now, because I've seen that before. That this was really fast before. Staring at that number, and now it's not, and nothing has changed. But it is that I have been filling up something in the REPL, some resource in the REPL. I don't know what. If someone in the audience know anything about it, I'm very curious. So now we have a fresh REPL. Actually, that's why Bensless sometimes adds that to his instructions to me. Bensless is this performance guru with Clojure stuff, and he tells me to do it with a fresh REPL. So I guess this is what he means. Let's see if that's. Now we have a fresh REPL. We load the file. Make sure that we compile this with uncheck math false, and we run. Okay, we haven't required that. So, and you notice that the first time we run criterium bench, it does a lot of this output.
Yeah.
And then this, when you run it a few more times, it gets less of that. So I'm not sure exactly, but something it does in the first round needs to be done. 2.8. Actually, don't understand why it would be 2.8, but.
That's the new number. That's probably something to do also with your machine. Might be.
Now we compile this again. Yeah, it could be, but we saw also 0.7 milliseconds when we had uncheck math. Yeah, you see.
Yeah. Okay.
Okay. So the way things are right now, we seem to gain a lot by using unchecked math. Instead. And I mean, check math means that it's checking stuff right before it actually does the math. So it's probably costly. But we also need to think a bit about what could the cost be of starting with giving it this. So that means that will translate to something like arrays.fill in Java. Maybe we can even see it here. No, we don't see it here, but somewhere down the line there it will do something like fill or something more costly than that. So this might actually cost us also to start with that. So we could also consider to reverse the logic here. So if we put false in this array for all primes, and then put true
I don't understand.
for them when they are not primes. So we can say true is because we won't be doing this filling of the array.
Oh, does it automatically set the Boolean array to the value to false?
So if you just like create a Java array, it will allocate some stuff.
Okay, so it'll be like null values.
And it will be like all be, and then if you want them true, then you will need to fill it with true. So you need to go through all 500 numbers and flip them.
Okay.
All 500 slots and flip them. And I mean, that's very quick and efficient thing to do, but we could figure if maybe it is costing us something to do that, because in a way the gains you get from like starting to tweak if it's unchecked math and stuff like that. I mean, that could be super important. But if you can tweak it on a more algorithmic level, right here. Okay, we don't fill it with truths first, and stuff like we stop at the square root. I mean, that's actually where you do the huge gains. Of course, we will not do such huge gain with this change, but it might be. So I was thinking that before we start fiddling around with helping the compiler, we could just see if we can help the actual code to not do as much work.
Okay.
So if we have primes here, and then that truth in this array will mean we have removed it from the primes. So it's a bit not as immediately. So we say when it's not set here, we will loop, right?
But doesn't that mean that
does that make sense?
But doesn't that mean that you're going to have to invert all the trues to false and all the falses to true at the end in order to get the right result?
When we loot it.
Yeah. Okay, so
when we loot it.
Even for the competition, it just needs some indication a prime is different from a...
No, the competition doesn't care how you represent the primes. You can represent them anyway, and you're allowed to return your representation of it.
As long as you can loot it. It's lootable.
As long as you can loot it. Okay. Exactly. As long as it does the right thing, right? So loot is like the proof that we're doing the right thing here. So here I think that's all you need to do. You don't fill it with truth here, and you change this to when not, and then we flip this to true every time. And then we of course need to do something in our loot function, because this one
the opposite,
will
176.
It wasn't very helpful error message.
No.
Unable to resolve symbol loot. We haven't. Okay, we have a fresh repo. Yeah. So that's the wrong answer, right? Because now we need to reverse
the logic.
This. What? So it should be
if I then
when is this when not? Is that simple?
No, but then what about the first one?
The first one is just that we always treat the index 0 as prime, right?
Okay. Oh, okay. It's if the index. I'm checking the value. I was thinking about the value. Okay. Looks
So
good.
this looks correct, right?
Yeah.
And let's see if we have gained anything by doing that. .7, I think it's running with unchecked math. It must, I think. No, now it's 2.4. So that's really strange.
Yeah, that is odd. I wonder if
So if we
put it back,
undo this,
yeah,
and yeah. So I think I've seen this improve the performance, but I think that we also need to consider what is being compiled from what code. So it could be that by doing the change we did, we were producing more of this
more logic.
runtime. Exactly that kind of stuff. So it could be worse bytecode from that. So maybe before we do that improvement, we could actually then look at how we can help the compiler with this. Should we make a version of this so that we can have it
with and without. Yeah, I think that there's an interesting point there, like where you think logically it should be faster, but it's not necessarily true.
No, and that's like the thing we was mentioned in the first video we did, right? It's very easy to assume things, and if you're chasing microseconds in some hot path of your code, you can't afford to assume things. You need to test and run benchmarks, and very carefully, just do one change at a time. Maybe we're violating that as well a bit here to just make sure that because at some point here you will gain less and less for each change, and you need something more dramatic in terms of change, because we are like chasing a local maximum now, right?
Yeah.
We have this way of the algorithm. We have the Boolean array that is the fastest of the data structures we have tried, and then when we're there, we're chasing like a local maximum. You stop inventing. Really, you're more like tuning. So then it gets super important to measure very carefully what you're doing. So if we have a version of this one that's called very verbose, like that instead, and you see that it's still doing the right thing. No, we're not doing the right thing. That might be why it goes so fast then. So
accounts off.
We saw it do the right thing for 100, and we looted it, right?
Yeah. So what do we get? Oh, we should have
and
it's for.
We counted what I've looted for 1 million. Oh, no, I don't know what I did. That's very good we're recording this, because then I can check what the hell I was doing when I got this.
421,503.
Okay.
Okay. I didn't see where that would have come from.
No, me neither. But if we what we're doing, but now we're just doing this checking when we were at 0.7. So of course it's the same. I just copied the function, and we can decompile this one here.
So by help the compiler, you mean like the warn on reflection errors. Try and get rid of the types.
Yeah, warn on reflections. You don't want reflection. I don't think we have reflection in this case, but you don't want that. And because we did set warn on reflections to true, right? And we didn't see see a warning.
Yeah.
But it's a bit strange because I think I should be type hinting this one and helping the compiler. But also these unchecked math and stuff like that. That's also will help the compiler to produce as native produce bytecode that translates to what the native Java, if you hand code it in Java.
Okay.
If that makes sense. So that's what I mean with help the compiler. So everywhere where we are calling the Clojure runtime and everything, that costs. So we want to do that as little as possible. And we certainly want to avoid doing it in the hot path. So we have the compiled code here. And what I mean with the hot path is we're down here, right? In this tight loop down here. And we're testing stuff. So down here, we don't want to do even unchecked int cast here and numbers divide. We don't want to do that. We want to do division in Java, right? Using the operator.
Okay.
That's what we preferably want to do. So that's what I mean with help the compiler. So we could. As I said, this is how you do type int. So this will tell the compiler that this n thing is a long thing. You see here it's a final object. So if we decompile this, it's a final long instead. So that should in if we put the REPL down there. So now we have that, and we run. Okay, I put too far. So that is now at 800. So that is about the same. Any particular gain from that, but we can understand that we want to be. Yeah, we see what it's doing. So the next thing we can see here is that it does this numbers divide with here, so it still thinks half n is just an object, right? It doesn't know anything about it. So we might want to help the compiler here again, and there we have some functions here. So one is called unchecked int, and what unchecked int does is coerce to an int, and it's subject to rounding or truncation. So it doesn't check stuff like that, right? It just
doesn't.
So if we do that on this instead, and then sorry, I was decompiling, but I was not compiling this. Let's try that again. Sorry, I don't think
so
we
you have to reevaluate it in the REPL.
Again, we can. Again, we can check that in the video if we did that mistake. But anyway, it feels like I'm doing it when I'm when you're compiling, when you decompile.
Yeah.
So yeah. Yeah,
Okay,
exactly.
that's still the same.
So anyway, that's where we're. It's still about the same. Yeah. Well, let's compile that,
Why?
or rather, let's decompile that. I mean.
So my question is like, why do we run the unchecked int function there on the divide by 2, and then not type hint half in as a long also?
I don't think you can do that.
Can't type hint there.
Let's see. Would we say that is long? Actually, it didn't complain. Let's see what it. Because now it's at final int here because we did that unchecked int. So let's see what it. It's still an object.
Okay,
I don't know. So at least it didn't do the right thing. So let's go back to unchecked int here. We can see that now it gets to be an int, right? So that's what we want. And then we have primes.
Oh, we could do the same thing.
And I see we have that is an object. I mean, that's probably fine that it is an object. And we have some unchecked int cast here on this number. So, I mean, it might be that the division is a bit special. Maybe there is some kind of unchecked divide int we can use.
Oh, okay, yeah, I see it. Just as a straight.
At least see it now. It does like that. So that's good, I guess. But we can do something better than unchecked divide hint. Actually, we can use a bit shift operator. So bit shift right. It looks like this in Java. And if we bit shift n 1 bit to the right, we just shift all the bits. So every bit position in a binary representation is a times 2, right? You follow me?
Yeah.
But then if we shift all the bits to the right, we actually divide by 2.
Oh, okay. Some Boolean math.
So look at that. So it will now bit shift n 1 position to the right, and no casting or anything there.
Okay.
So, I mean that's really good, I would say. And then we see. Okay, let's see if we have gained some.
Yeah, I'm curious.
Some performance there. I'm not sure we have, but we could. And about the same. We need to do more of this because we're down here in the hot path. That's where the real gets really interesting.
Yeah.
So the square root here of that could be checked long instead. I don't know. It says final long here, but we do like
this
that.
Long cost.
You see, I got rid of this.
Yes.
So that's good. But now we are doing a double cast here. So we can probably, let's see, and check double. So we got rid of check double there. So more could we do
So
here? We could. Yeah, sorry?
No, sorry, I was going like in the hot path now, but there's actually like
My experience is that you can often like reach the hot path by making sure that your bindings have the right thing.
Oh,
and
interesting.
The compiler will often do the right thing down there. So we have a Boolean array here, which is unchecked int on half n, I think. So did that work?
No, did it do anything?
No, it actually was already
because it's
correct there. So let's undo that. Didn't do it
because that's been done
difference.
before. No.
Let's see that we still do the right thing. The code before we go
Too
crazy.
Yeah.
And it seems like we're doing the right thing still. So 785. We're still not reaping the benefits that I'm hoping we should be able to. But we can continue. We saw here up here how bit shift was much more. It is a super fast operation in Java to shift some bits. I mean, that's super efficient, but also it helped the compiler to just figure out that these are just regular int. It shouldn't be
objects
using the Clojure runtime or anything for it. So it's so we could do the bit shift right here again, and decompile that. You saw that's pretty dramatic. But now we're closing in on the hot path here, right?
Yeah.
And then we have the same thing here. Shift right.
Okay, now we have to see some real benefit after.
Look.
Yeah.
Do you see any calls here to the Clojure runtime except a set? I mean, you can't really do that one.
Yeah, you have to.
It's, So if we compile this and we check that we're still doing the right thing, 39 seconds. Very strange. But the loot is taking time. Yeah.
Yeah. Okay. Wow. And that's what
we're down here in
for a while.
Almost half a millisecond. Where we are here. So I think this is about where I have reached so far with this work. So as I said, beyond this, it's hard to see here how we could get cleaner code than we get here. I mean, cleaner Java code or byte code then. And it's also hard to see how we can improve the algorithm. I mean, it has been what it is for, I don't think, Eratosthenes was 400 BC or something like that.
Been like that for a while, yeah.
Can probably not. Yeah, so we can't do very much there. But again, it's the data structure. Now we are manipulating Boolean array. We should be very, very constant time, right? But probably we can make our own data structure to do these operations even faster, because we won't be we won't have to consider everything that that Java needs to consider when it flips an array position. If we would do this, we could be much more raw if we would do it in our own structure. I think at some point I might actually go down it because it's exciting to think about creating your own data structure. I have also tried this with the bit set, Java's bit set. So I wish I could use Calva to show it, but something wrong with Calva right now, so I can't look at.
Let's complain to the guy who makes it.
yeah. Acceptable here. And so this is the bit set data structure that's built in to the standard library in Java. And it has things like flip, set, and clear, and it also has things like next set bit. So I imagine that next set bit should be faster than looping and see is it set, right? It should be doing something more efficient. Next set bit on the bit set. I haven't succeeded there. Actually, I get about half the performance from a bit set that I get from the native array. And Blend/Less has promised me to tell me why. He knows. But if you look at the source code for bit set, you can at least see that when you call set on it, it does a lot of checks. But it does checks, right? Before it does it. And I guess it's very general data structure, a bit set. So it needs to cater for a lot of use cases and stuff like that. So it needs to do a lot of stuff that we wouldn't need to do if we made one ourselves, right? Then we could just like cheat our way. Say, okay, we're only going to use it in this particular way. And then we could create our own bit set that doesn't do all these checks and stuff like that. So I'm very, very curious about Ben's take on why it's slow, but it is slower, and so that's something else. What's speaking for a bit set is that what's the difference here between a Boolean array and a bit set? Would you say? Actually, that's a bit of a mean question because
and I don't.
We have a Boolean array. Actually, but given where we are here, it is that with a Boolean array, you would assume that each Boolean takes up 1 bit of memory.
Yeah.
I mean, that's easy to. I mean, it's just a Boolean, right? How much place should it take? But actually, it takes up 8 bits memory for. I don't know if it varies between how large the array gets. So if we would code the Boolean array version up here, we would have to say that it uses 8 bits.
Why is that? Do you know?
If we look at in this competition here, for this that Dave Plummer set up, he has like different categories for the competitors. So one category is how many bits per prime are you using? I mean, because if you would save primes, like we're only doing 2 million now, right? If you would save a prime up to billion or gazillion or whatever, then it would start to matter if you use 8 bytes or 1 bit per prime, right? So that's actually count in this competition. You need to use just 1 bit. So the closest I'm using here, you see the bitset for this solution here, and it's
There you can see it's slower.
much slower
Yeah.
than the Boolean array. But here I have this like taint on this one. It's an 8, so it won't count. So if they would pick up Clojure in one of the plumber's videos about this, they would pick this bitset one up right now. So in order for Clojure to climb in this composition, I'm filtering it now on Java and Clojure. Then we would need to do something that uses 1 bit, and then and this one, to beat this one, we need to create our own. I think that's the only thing we could do. I'm rambling on here, but these are the things that go through my head when I look at this performance problem.
So this is the fastest you've got it to now, using this Boolean array, and then helping the Java compiler and keeping the logic the same. Well, you haven't changed the algorithm.
So we haven't tried this on this version yet here, right?
No, let's try that before we
changed.
Yeah.
We changed the.
Oh, sorry.
Not. And we do that, and we said we needed to do when not here, right?
Yeah.
And time that. Still doing the right thing.
Yeah.
And we're down.
Let's end on a win here.
So it's about the same. But,
yeah.
At least now we're not losing.
Yeah.
This way. So something about us not helping the compiler might have caused it to create something a bit crazy when we did this logic change before. So this is super. Well, let's look at what it does. Now we're only changing the logic here. We saw this check got to be not here.
Yeah.
So this is how efficient I think that the Clojure compiler is. It's actually pretty amazing.
Yeah.
The work it does. So.
Yeah.
And we were a bit curious also about why this didn't help so much before.
Wonderful.
Right? So if we do that, you get back a lot of the Clojure runtime stuff here, or I don't know if that's called Clojure runtime, but there's also Clojure in there. And let's see here now if we, because we didn't see so much different before, but I'm assuming that we should actually, because that's my experience here. That type hinting is one of the easiest way to help the compiler. No, you don't get it. It's this doesn't cost very much to do it on this level, because this is not just doing it once.
Yeah.
So we are probably beating the type hint help here by doing this help to the compiler ourselves here.
Yeah, I mean, it makes sense that, like, in the loop where you're looping over stuff millions of times, that's where you're going to get the biggest benefit.
Yeah, and you need also to consider, so performance is one thing. How much memory you consume is also very, very important. But then, as we talked earlier here with our audience as well, readability of the code is also very important. And bit shift right n1, it's a bit harder to read than divide n by 2, right?
Yeah.
And you have this unchecked int here, so it's more code now. So if Rich Harris look at it, it's not more lines of code, but it's more words, so more bugs.
Yeah.
So it's there's a trade-off. You want to do there. And the point I was wanting to make, so it's type hinting to help the compiler at one place with just one word there. It actually helps yourself also looking at n and see that it's long. is sometimes enough that you can sacrifice for performance, instead of doing all this kind of funny stuff in the code. So this is when it's super important to get the performance. Then you do this kind of stuff, and I mean, it's a competition. So how much more important can it be? Right?
Yeah. Well, yeah. It's not. No one's reading the code here.
I would kill kittens to do it. Right?
Yeah.
But anyway, so I think that it's easy to go very far with performance tuning like this, and we have been focusing on performance. Just wanted us to not leave the impression that you should be doing this with your Clojure code in general. A lot of Clojure code is not about crunching numbers and mutating some very flat data structure over and over again in some hot path, right? It's more about transforming one type of data to something else, enriching data, and that calls for super readable and code, and as little code as possible, I would say, to get that right. And also you will get performance, because that's what Clojure is built for. Yeah. So, but sometimes you need it, and then you should do it, and you should know a bit of what you have in the toolbox. And I'm so happy that I've started to do this and started to ask people with much more knowledge about it than me in the community, and I have done so. So I can really recommend doing the exercises and having this, sharing this kata with me, because it's really fun and you learn a lot.
Well, I'm glad you've done it, because we got to learn a lot from you by doing it. I think I'm going to call this in the stream here. This has been really cool.
So thanks for watching, everyone. It's
thanks, guys.
Super fun.
And all the code and everything is in the description. This has been really cool.
Yeah, so
if you want to make Clojure
I will push this latest
way. Cool. Thanks a lot, Peter.
Thank you, Daniel. Thanks for having me. Super appreciate it.
Cool. Till the next one. Cheers.
Till the next one.